Hello, everyone, and welcome to our first HMS quarterly webinar of fiscal year 2024. My name is Avital Breverman. I'm part of the HMS team, and I'll be introducing this webinar today, so thank you for joining us. Today, you will hear from three presenters, Dr. Jay Pack, David Ho, and Daniel Black, and they will talk about debris yield, sediment, reservoir reduction, and post-wildfire capabilities in HEC-HMS. We haven't presented on those topics in a while, so I'm really excited for this one. And before I turn it over to the presenters, I just want to remind you all that you are all muted to minimize disruptions. If your dog starts to bark enthusiastically about hydrology, we won't hear it. We are recording this webinar, and it will be posted to our website later this week. And on that topic, I'm just going to remind you all of our website and the resources available to you. So I'm on HEC's website. You can get to the webinars by selecting training material. And then you can select the COP webinar series, that is this quarterly webinar series, our HMS quarterly webinars. We also have a separate webinar link for other HMS related webinars that various team members deliver. And as a reminder, we have a lot of documentation available to you under our documentation tab. If you visited our documentation site in October, and it wasn't working, we apologize, it is now up and running. And you'll hear more about documentation from our three presenters. So with that, I'm gonna turn it over to Jay.
Thank you. Let me share my screen. Okay. I think now everybody can see my presentation mode screen. Okay, thank you for introduction, Avital. So, hello everyone, I'm Jay Pack. I'd like to apologize in advance for my potential coughing during the presentation because I have some coughing issue now, okay? I will briefly introduce some of the new features in HEC-HMS, especially focus on post-wildfire hydrology and debris flow modeling. Okay. After that, Daniel and David, they will present, demonstrate the two case study for each specific case. First one is a technical transfer material and documentation. Recently, in this year, we did a two-time workshop. Okay, first one for district engineer, and in April 2003. And the second one is the last month for California DWR. So it was great. 2-day HEC-HMS and 2-day for HEC-RAS. You can download the whole information, including slide and some workshop material, everything inside this link. You can download this link. And then also other related, some tutorial guide related to post-wildfire hydrology and debris yield. You can find some of them from our tutorial guide. Okay, now I want to present some general debris yield process in HEC-HMS, overall process, and then I'm going to go over one by one. It means each element, so basin, reach, reservoir. This is overall process, sediment and debris transport process. Originally, HEC-HMS, we have only regular sediment, surface erosion. But based on the, I think since the last 4 year, we got some research fund from the CHL, and we developed this specific debris yield and post-wildfire module in HEC-HMS. First one, inside watershed mean is a sub-basin element. We have 5 options to calculate the debris yield. First, the 4 option, just a function of rainfall intensity. This is more emergency purpose because we don't need some post-wildfire runoff information. But if you have some more detailed information for generated surface runoff under the burn condition, you can utilize LA debris equation 2 to the 5. Okay, you have a 5 option. And then another one is a post-wildfire dynamic infiltration loss method. After fire, we have some hydrophobic layer. With that layer, our infiltration loss rate is decreased a lot. But through the time, through the event, is gonna be increased up to unburned condition. We can simulate this situation for long-term, at least 10-year dynamic infiltration loss simulation with this function. Inside the channel, traditionally, we have just a 7 transport capacity method that is just for river sediment. But it's not working properly with the hyperconcentrated, like a debris yield situation. That's why we add the sediment delivery ratio. It's a simple hydrology concept, but you can control manually erosion and deposit inside the channel. Okay, and then after that, channel outlet, it's not like HEC-RAS. We don't have a fine cross section. We have just a reach element. Then we cannot just dump sediment, suspend sediment to the next control volume. That's why we're using this sediment routing. And then we added Muskingum to control the attenuation and a lag. Okay, inside the reservoir, we have 2 options for trap efficiency method, chance or balloons. You can calculate some deposit amount with this option. And then we can update it, elevation area, elevation storage curve every time step. Then we can continuously update it, our volume reduction for reservoir capacity. Okay, that's just something, overall process. Let me go at data side. Data, okay, to simulate this post-wildfire debris yield and post-wildfire hydrology, you need rainfall data. And then you need also topographic data, and then soil burn severity map. Normally, you can get the from the Bear team. And then soil gradation curve, specific gradation, gravity, and then density. Normally, you can find the data information from the actual sample at your site, but you don't have a chance, then you can using G-Circle data to estimate this value. And then also you need the gauge data, pre and post, for calibration, for validation. And then finally, you need the debris measured amount for your debris yield analysis, calibration, and validation. Using this information data set, you can fill out the required input parameter. From the basin model, you can go to sediment tab, you need a specific gravity and then density for each grain size. For sub-basin element, from your erosion tab, you need to put some relief ratio and the burn percentage and the burn date. Also, you need to put the gradation curve. That's just normally you can find this sample from the outlet of your watershed. Okay, and then reach element and some in the sediment tab, you need to put some reach element gradation curve, also some cross-section information in here. How you get this data? Maybe you have a lot of source to get that kind of data, but I want to recommend this NASA Recover site as a one-stop shopping. Okay, this is a new site developed by Idaho State University and NASA. So you can find the whole information, fire map and the terrain data and the G-Circle information and even rainfall information, all of the information in here. This is a recent fire, Maui, Hawaii fire here. So I asked, because they just covers in a continental area, not the outside of U.S. continental. But I asked to them, and then they, generate Hawaii fire information also too. Just kind of check this site first, just to save your time. And then if you don't have that information, then you can go another source. This one is a GUI for debris yield. If you want a debris yield analysis, go to sub-basin tab, and then you can choose one of debris yield method. After you choose the one of them, and then HEC-HMS generate a specific kind of interface for each method. And then you need to put some required input parameter for each different method. And then HMS generate information result. This is a result graph. This is a sediment volume, sediment concentration, and the sediment load, and also HMS generates some summary table. Okay, with this, you can generate some boundary condition, input boundary condition for HEC-RAS. Okay, HEC-RAS, two options. You can use this bulk flow. Bulk flow means is water volume plus sediment volume. So they can directly link this kind of time series DSS result. Also, from this summary table with water volume and sediment volume, you can generate it working factor. Then you can put the working factor into HEC-RAS directly. Okay, and then next one is a rich element. Rich element. Originally, we have a 7 transport capacity, but that is not working for hyperconcentrated system. And then that's why we need some simple but manually controlled erosion and deposition, especially in the steep channel inside mountain watershed. Okay, this is a simple concept. Your input sediment amount for your reach, and then you can control sediment delivery ratio, then you can get some outlet. Okay, if you choose some 1 for sediment delivery ratio, that means input and output sediment is same, is equilibrium condition. Less than 1 is a deposit condition. Bigger than 1 is erosion condition. That's you can control the deposit and erosion inside your channel. Okay, this is interface here. Let me use the radio point here. Okay, this is interface. You can choose each grain size sediment delivery ratio. Okay, to control the volume. But after control the volume, you want to control the translation and attenuation. This one is you can easily control the Muskingum routing method with the 2-factor attenuation coefficient and the travel time. Then you can control attenuation and the translation and the volume with this SDL and then Muskingum routing, debris routing method. Next one is a reservoir. A reservoir element, you can see this big picture here. This is the San Bernardino County Deer Creek debris basin. Debris basin intake tower, this is inside the basin. That is after fire, but before storm event. But after Christmas storm event, you can see there's a huge debris yield already filled by this debris basin. We need to simulate this one with HMS, okay? For large watershed, a large reservoir. This is one of example. This is a time vertical, horizontal is time, vertical is volume, reservoir volume. Through the time, by the siltation, reservoir capacity is reduced. But after fire, is kind of dramatically reduced some reservoir capacity. And then normal time, and then after fire. During this kind of whole long-term time with the fire, then reservoir gonna lose some capacity. Then we have to raise the dam, or we need some kind of flushing or dredging. But we want to do some simulation with such model. Okay, I think Daniel Black is going to demonstrate first for long-term big reservoir. But unfortunately, this case study, we don't have a fire event. But you can see somehow work this reservoir element in terms of a volume reduction capacity. This one is some kind of a process. HEC-HMS calculated trap efficiency with the chance method or balloons method. With that, we can compute the siltation amount and then updated elevation storage, elevation area curve. With the updated elevation area curve, we can update it, calculated critical velocity, and then we can get the updated chance trap efficiency method. With this kind of a process, we can continuously update it, elevation area, elevation storage curve. Top of that, we have 2 options. How we can update this elevation storage curve, okay? You have 2 options. First one is a V-shape option, meaning it's a deposit from the bottom. And the second option is elongate taper option. It's going to be deposit from the upstream. For example, this solid green line here, this is a prior siltation. But if you choose the V-shape and then the dot solid dot green line, is it lose the capacity from the bottom. But if you choose some elongate taper, like a yellow solid line, you're gonna lose the capacity from the upstream. But you can choose this option by grain size. And then you can control this your elevation area, elevation storage curve to update your reservoir. Okay? This is interface. User interface for reservoir, you can choose this Bruins trap efficiency, chance trap efficiency from the sediment method. Okay, each method has its own component editor. You need a required input parameter, and then HEC-HMS generated cumulated debris yield or sediment yield, or elevation area, elevation storage curve updated by monthly. Okay, this is one example. We're using 4 different debris yield methods, and then with that, HEC-HMS generated cumulated through the whole storm season about the 4 months, and then this orange line, solid line is measured data. Everything is pretty close to with the major, but they're different by event. Okay, this one is just something continuous accumulation information. Another graph here, elevation storage curve. First one is initial storage curve, and the last one, this is a final one. We updated, we provide the monthly. Okay, for elevation 270, original capacity about the 110,000 cubic meter, but after three and a half months, one storm season, you have just only 45,000 cubic meter. This much you lose already. So with this information, you can control the debris basin management with for future kind of debris yield event based on the forecasting information. This one is ensemble analysis tool. And many people asking which method is best. Without some data to calibrate and validate, it's hard to say which one is better. But normally, emergency situation, we don't have a data set for calibration. So for alternative suggestion, maybe you can just using 4 all debris method, and then using ensemble analysis tool, and then we can provide some range. It's a maximum, mean, minimum range. Okay, you can provide this range to the HEC-RAS for your some non-Newtonian simulation. Okay, David Ho is going to present more detailedly with his kind of case study. And then this one is another application with the HEC-HMS 2D. I just connected some maximum debris yield as kind of a bucket flow into 2D boundary condition, and then generated some inundation mapping. But this one is just for clear water. It's not non-Newtonian. But before using HEC-RAS, you can get some idea with some try and error, and then finalize some your alternative, and then go to HEC-RAS, and then make some final simulation with a non-Newtonian simulation to get your final boundary line for your debris yield. Okay, for next one is a dynamic infiltration loss method. This graph, I got the 2020 Brian Abel paper. So after fire, he took some measurement, hydraulic conductivity. The first one right after fire, and the second one is 4 years later, like that. You can see that some hydraulic conductivity increase from the fire up to certain unbound condition. Okay, we want to simulate this one for long-term post-wildfire hydrology. That's why we add one surface layer to control some dynamic infiltration, and using this dynamic infiltration loss method. Okay, this KS initial is this initial, just right after fire. But this with decay factor is gonna be improved until up to unbound condition hydraulic conductivity. Excuse me. This decay factor is a function of a burn percentage, and the function of time, also a function of event. So with this three parameter, decay factor is increased up to unburn condition. So let me show you some example here. Red one is with the dynamic infiltration loss. Bottom one is without dynamic infiltration loss, up to 9 years. You can see the first year pretty close, about the 0.77 and 0.7. But through the time, without the dynamic infiltration, is a net subscript coefficient is pretty low. But this one is still not bad. It says 0.2 is not good, but still much better than without dynamic infiltration loss. You can see this is a final result with the 3-year simulation is a percolation. So you can see the light blue, the percolation is low, through the time is increased. But it's kind of a blue line is a dark blue is just keep the same without the dynamic effect. Okay, that's some way to using a dynamic infiltration loss method in HEC-HMS. Okay, future plan. This year, I'm concentrated this new feature because for post-wildfire hydrology, many people using curve number loss method because we have some good guideline from the USDA hydrology technical note number 4. They provide the curve number before fire, after fire. And even after fire, they provide some minor burn, moderate burn, and severe burn. And then many people using that guideline to generate the post-wildfire condition hydrology. But that is not site-specific. That is not the physically based. That's why our soil scientist from the CHL, Dr. Schlitter, and then from the DRI, Dr. Burrell, they kind of suggest that this modified green NM. Modified green NM is just replaced wetting front suction. This is original green NM. They want to just replace the wetting front suction value with the subsidy value with this Phillips equation. After replace this Phillips equation, that we got a new updated modified green NM method. That's the function of hydraulic conductivity and subsidy value. Why we need to do that? Because the subsidy value is easy to measure at the field from the burn site. So easily we can go to site with this O-ring and then put some water 1 centimeter and then take some time. Then we can get that value and then utilize to the post-wildfire hydrology a little bit more kind of a site-specific or a little bit more physically based. And then still Dr. Schlitter and Dr. Burrell, they trying to provide some guideline, okay, based on the different texture, soil texture, and then they trying to provide some range for subsidy value. This is unburn subsidy value. This is burn, but with a different category: low burn, moderate burn, high burn. But this is still working on. It's still construction. They trying to update it. But with that, we can provide another alternative way to calculate the post-wildfire hydrology. And then also we can compare with SCS curve number approach. I think this is my last slide. Next, I think Daniel, he's going to present dynamic volume reduction application for reservoir long-term simulation. And then David Ho is going to present ensemble analysis application. So Daniel, I want to hand over to you. Thank you.
Okay, thank you, Jay. Okay, so I am going to demonstrate some of the updates that Jay was just talking about, particularly the dynamic reservoir volume reduction feature. So What we see here is a very simple HMS model. We have a source element, a reservoir element, and a sink element. We're going to open up the component editor for the reservoir, and you can see that the sediment method is set to the Bruin sediment trap, which Jay was just talking about. So going to the sediment tab, we can see the component editor for this particular method. We have these parameters that we have to provide, and then we have two boxes here to choose a reservoir capacity method and a deposition shape. So setting the reservoir capacity method, it's a yes or no option. Setting it to yes will update the elevation storage as well as the elevation area curve each time step based on reservoir sediment deposition. Setting this option to yes allows you to choose a deposition shape. As Jay was showing, we have V-shape and elongated taper. The important thing to note here is that with the current implementation, looking at the four grain sizes, clay, silt, sand, gravel, regardless of which option you choose, clay and silt are automatically deposited using the V shape, meaning everything is deposited on the bottom. So with some updated code that I'm showing in this demonstration, selecting elongated taper also sets clay and silt to use that option as well. For additional work that we're looking at, we would like to be able to select deposition shape for individual grain sizes. So in the interest of time, we're going to assume that I just ran a compute and we're going to look at the results. So I'm going to expand this a little bit. We're going to look at the simulation, the reservoir element, and the sediment folder. And these are the sediment results that are available for the simulation. So the sediment load, let me expand this a little bit. The sediment load is the outflow of sediment from the reservoir. We have the breakdown of individual grain sizes. So you can see gravel is essentially non-existent. Sediment volume is the given in acre feet, that's the volume coming from the reservoir. Bulk flow is the combination of sediment and water volume. The combined sediment load, as well as the combined sediment volume, these are the load and volume of sediment coming in from the source elements. In this case, we only have one source, so it's all coming from source one. And then, same thing for combined bulk flow. That is the combined bulk flow coming into the reservoir. The more important ones that we're looking at are the bottom sediment. This is the sediment that gets accumulated at the bottom of the reservoir over time. This particular simulation, it's a long period of record running from 1972 to 2009, and you can see the accumulation of sediment over time. And then finally, the suspended sediment. This is sediment that is suspended in the column after deposition occurs. This sediment will eventually become outflow or additional deposition given enough additional time. So we're going to look at the results a little more closely. So I'm going to pull up the DSS file for this simulation. And I'm going to filter down to elevation storage. And here are the results for our elevation storage. I don't know if you can make out the text here. Each record is a 1 month period. Results are calculated monthly by default in order to prevent inundating you with data. A 1 month time step is plenty for looking at reservoir volume reduction. So in this case, I'm going to select the first record from 1972 and the last record from 2009 and plot. The green line is our 1972 curve. The red line is our 2009 curve. The x-axis is the elevation given in feet, and the y-axis is our acre-feet storage. So if we look at a point here, say 1,100 feet, we can see that in 1972, our storage was about 909,000. And in 2009, our storage is around 732,000. So we can see that over time, our storage volume is being reduced. Now we're going to look a little more in depth at the data. So I have a spreadsheet. Again, I don't know if it's large enough font to read, but we have two tables. The first table is our elevation storage curve based on survey data. So we have the 1972, 1983, 93, 2000, 2009, and 2020 surveys. And the second table over here is the change. The change is calculated for a given year by subtracting the 1972 volume from the whichever volume you're looking at the change for. So in this case, let's say 2009, we would subtract 0 from 839. So that's where that's where this data is coming from. This particular graph is just a plot. Let me zoom in a little more on that. This is just a plot of all of the data in the columns we were just looking at. And we're going to focus on the 2009 curve, which is the one in blue here, because that's what our simulation was showing. And let me change this. Okay, so this is our 2009 simulation. And the first two lines that we're going to look at are the blue and green lines over here. These represent using the current method that's in HMS, the deposition shape, where the elongate method is only depositing sand and gravel in an elongate shape, and silt and clay are still using the V shape. And we can see that these lines do not match very well with the measured curve from the 2009 survey. So if we go ahead and turn those guys off, so now with the updated code that we are testing out, in this case, the elongate shape, all grain sizes are using the elongate shape, and so the orange line here represents using the Chin sediment trap method. The yellow line represents the Brune sediment trap method, and the green line is our measured actual surveyed data. And what this shows us is that, with the proposed changes, we are seeing a much improved matching of simulated with observed data. This backs up the idea that having the ability to model grain sizes individually would probably further improve our calibration results. So the key takeaways from this demonstration is that setting up the HMS model to model volume reduction is fairly a fairly easy process. Going back to our component editor, this is a very easy component editor to parameterize. These results track very well with the results produced by HEC-RAS. So I'm gonna pull back. This is not an actual table in here. This is just a screen capture. But the results in blue represent those produced by HEC-RAS. The gray represents HEC-HMS, and you can see that the results track very closely. So there is some advantage to using HMS, given how easy it is to set up the model. Another important takeaway from this demo is that the model that I'm demonstrating, the long period of record, doesn't include post-wildfire sedimentation. So these improvements are not just geared towards post-wildfire. These can be used in any case that we have a reservoir that we need to model sediment on. And then finally, a lot of this work came about from needs from modelers in the field. Before these capabilities were added to HMS, people would, modelers would have to use a spreadsheet kind of similar to what we're looking at now. Modelers preferred using spreadsheets over setting up a RAS model, and the issue with that is that even an Excel sheet can get kind of cumbersome when you're dealing with 60, 80, 100-year period of record. So I mean, you can see this table here. It's annoying to look at. It's hard to make sense of. So HMS is a much more concise way of modeling volume reduction. So yeah, that's pretty much the end of my demonstration. I believe David is up next.
Thank you, Daniel. All right, so hi, my name is David, and for my demo, I'm going to show how you can use the subbasin debris yield methods that Jay had talked about to generate a bulked flow hydrograph. So, so Jay had mentioned that we had debris yield methods that can be used to estimate debris volumes. So we can incorporate the debris yield volumes into our clean water hydrograph. So this is useful if you need to estimate the potential increase in your flood after a wildfire event on your watershed, where previous ways of estimating bulk floods has been simply just to multiply your hydrograph by a factor. You can still do that in HMS, but we can also incorporate the volume of the debris into the hydrograph itself. All right, so for this demo, I'm going to use the Grand Canyon watershed that's located in Southern California. We have this watershed as well as its tutorials and guides on our Confluence page. So if you are interested in following along after this demonstration, you can go into our tutorials and guide space. It's called Task 2 Debris Yield Modeling Without a Debris Basin. So everything that I'm talking about is actually going to be coming from this tutorials and guides. All right, so as Jay had mentioned, we have 5 debris methods. For this demo, I'm just going to focus on the LA equation 1. So we have a watershed here that's been delineated in HMS. So to get started with the debris yield, the first thing that we check is at the basin level. So here we are at the basin level, And over by the component editor, we have this sediment. So we just want to make sure that it's selected to yes. When it's yes, you'll see this tab over here called sediment. So this tab here allows us to define the sediment attributes. So Jay had kind of brought this up. The ones that are important for the subbasin debris yield are the specific gravity and the densities. You also have the option to select from different grade scales, which is a selection over here. We have two options for you. So we have the clay, silt, sand, and gravel. And then we have one called AGU20. So AGU20, this offers 20 different grain sizes, which is a subset of the 4 grain sizes that we have here of clay, silt, sand, and gravel. For this demo, I'm just going to select the clay, silt, sand, gravel. All right, so next, we're going to head over to our subbasin, where we want to generate debris yield. So in the component editor, under the erosion method, we have all these different methods to generate sediment. And so we have methods like the modified USL, which is a very popular sediment equation. Since we're interested in debris yield, I'm going to select the LA debris method. And when we select that, we're going to have this erosion tab that shows up here. So I'm going to click on here, and here are the parameters for the LA equation 1. So each debris yield method will have its own set of parameters. Although if you were to cycle through the different parameters, you'll see that it's pretty consistent with one another. Our user's guide goes into much greater detail on what each of these parameters means. I'll go into some brief description for the LA equation 1. So this AT factor is the adjustment transposition. So this is if you apply the debris yield equation outside of its regional area, you would need to make an adjustment in that case. Since Brand Canyon is located within the area the equation is developed, I'm going to stick with the default value of 1. The relief ratio is the difference between your highest and lowest elevation. So this parameter, what's great is because we had delineated this watershed within HMS, we can go into our parameters, characteristics, and get our characteristics for our subbasin. So here, over in the subbasin characteristics, you can see we have relief ratio, which then we can take this information and apply it over to this parameter. Just be aware of the units here. So this unit is dimensionless units, whereas this one is meters over kilometers. So we have to multiply by 1,000 to parameterize this. Our next parameter is the fire factor method. There are 2 methods that you can choose from, the user specified fire factor and the pack and lead. So with the user specified, you just set one value. It's a value between 3 and 6.5, according for the LA equation 1. And then the pack and lead, this selection allows you to dynamically change your fire factor based on the burn percent and the dates that the fire was contained. So as you move further in time, the effects of the fire are diminished. So in this example, I'm going to use a date of September 2002 with a burn percent of 90. Our next parameter is the flow rate threshold. So this is a HMS specific parameter that was added to the LA equation 1. The purpose of this threshold was to allow for multiple debris generating events. So if you were using the LA equation 1 as is, you would only get one debris generating event. This threshold allows you to have multiple events that generate debris. So to illustrate this, so let's just say that this is our simulation window. This red line would represent our flow threshold. And what it's doing is every time the simulated flow passes this threshold, a debris yield event is triggered. So here, if we were to use this simulation window with these events, we would have 1, 2, 3, 4, 5, 6. So 6 debris yield events generated. So for this demonstration, I'm going to use a threshold of 1.7. And then our last parameter is the gradation curve. So this defines the grain sizes within your subbasin. So you create the gradation curve through the paired data diameter percentage function selection. So heading over to the table, you see here, you would set the diameters of your grain sizes as well as the percentage of those grain sizes. Okay, so I have a percentage function created, so I'm going to select that. All right, so at this point,
just comment, you put the sum 1.2 exponent portion, not the flow rate threshold.
Oh, thank you. Thank you for clarifying that, actually. That's important because I did miss the exponent. So the exponent, this is also another HMS specific parameter. What this does, it controls the shape of the sediment time series. So the sediment time series will be the same shape as the hydrograph if you use a value of 1. A value greater than 1 would make the sediment time series peakier. And then a value less than 1 will flatten the time series. So for this demo, I'm just going to use a value of 1. Thank you, Jay, for that, for catching that. All right, so at this point, I have finished parameterizing my erosion. I've also already set up the parameters for loss and transform. And so I'm ready to just run a simulation. All right, so you'll notice here that the simulation actually performs twice. So the first time it runs, it's actually computing the flow. And then the second time it's running, it's then computing the sediment. All right, so now we have results. And heading over to our subbasin, we can see the results. This is for our typical clean water results. We can see this is what we're used to looking at in HMS. And then with the sediment, it's going to be located in this folder here. So very similar to what Daniel had just showed. The sediment is broken down into weight, so a load value, and volume. And then it's also broken down into its individual grain sizes. So we have results for both the silt, sand, and gravel. You'll notice that for clay that we don't have any results. And that's because in our diameter percentage function, we didn't specify the diameter size for clay. So clay sizes are generally 0.025 and smaller, and we have nothing specified there. So that's why we don't see any results for clay. All right, and then we can now move on to our bulk flow. So the bulk flow has been mentioned a couple of times that it's a combination of the sediment volume with our clean water flow. All right, so expanding this, here, what we're showing here is the clean water, which is shown in this dashed line. The bulk flow is the solid blue line, and then the volume, the sediment volume, is represented in this red line. So as you can probably tell, the bulk flow is taking the sediment volume, converting it into a rate, and then adding it to our clean water. And that gets us our bulk flow value. So what you can do, as kind of been brought up by Jay, is you can take this bulk flow and you can pass it over to your hydraulic modeler for them to model the flow as non-Newtonian. You can, as has been brought up, you can calculate a total sediment concentration that you can also pass over to your RAS modeler if that's kind of the preferred input for them. So to do that, we head over to the global summary. So I clicked on the global summary, and then we got this global summary table that showed up. So I'm gonna switch it over to meters cubed, and so you can get the total sediment volume from this table here. So here is the sediment volume, and here is the clean water volume. And to calculate the sediment concentration, it's simply just taking the sediment volume and then dividing it by the clean water volume plus the sediment volume. And you'll get a % concentration, which then you can also pass over to your RAS modeler. Okay, the last thing that I wanted to demo is the usage of the ensemble compute type. So as mentioned by Jay, a question that we do get is like, which debris yield method should you use? So the answer, like all good answers, it depends on your region and your use case. So the debris equations, these are empirically based and will depend on your location, data availability, and your time duration. There are times, though, where this answer is not as obvious, and each method could be equally valid. So instead of making a decision on the best estimate, you can just assume that each method is equally valid and run them all together. So this is where the ensemble analysis can come into a play, where you can model the different methods independently and then combine the results. So to do that, we go to the compute menu and select Ensemble Analysis Manager. So here I'm going to create a new ensemble analysis. I'm going to click Next. So I've already created the 4 different debris yield methods, and I've run the simulations. So I'm just going to select these simulations together and then click Finish. And so that creates our ensemble analysis. So the last thing that we need to do is select the outputs that we're interested in looking at. So by doing that, I'm clicking the cogwheel, and this results window will show up. I'm going to come down. I'm just going to select the combined bulk flow. I'm going to save it and then close it, and I'm going to run this ensemble analysis. So what this ensemble analysis is essentially doing is it's running all of the simulations in sequence and then combining the results together. So here we are just finished computing the first and second simulations, and now we're on the third, and now we're computing the fourth one. All right, so we've finished the compute. So we can now take a look at our ensemble results. So we had only selected the combined flow, which is why we only see combined bulk flow. But we can see here, so we can see that it's computed each of the simulations. But in addition to that, it's also computing some statistics for us. So it's computing the mean of all of the computes, the mean plus standard deviation, a mean minus standard deviation, as well as a min and a max. So how you can utilize this information is you can provide to your RAS modeler a min, max, and mean value, which can represent your best case, your worst case, and your most likely case. Or what you can do is, if your RAS modeler is doing any type of calibration on some type of stage, what you can tell your RAS modeler is, hey, here's my hydrographs here. You're allowed to make adjustments to the bulk flow between this min and this max value, right? And that way it gives them some range that they can use for their calibration effort. Right, and then one last thing that I wanted to show was our ensemble viewer. So this is a new tool that is going to be available to you in HMS 4.12. This viewer allows you to view ensembles and different metrics. So to access the viewer, you simply go to the tools and then ensemble viewer. So when you click on this, this viewer should show up. So what I'm going to do is I'm going to navigate over to the DSS file where our ensemble analysis was computed. Give me a moment here. There we go. And so this is showing the same results that we just saw in HMS here. So it's the 4 different debris yield methods. So you can compute the min, the max, and the average. So this is very similar to what you had just seen in HMS. But what's unique about this is you can now select your own percentiles. So let's say you wanted to see what the 10%, the 50th percent, and the 90th percentile was. You can compute that. And you can see those results in the viewer. Okay, at this point, that's the end of my demo here. And I'm going to pass it over to Avital for any closing remarks and questions.
Great, thank you, David, Daniel, and Jay. Like I put in the chat, we have a few minutes for questions. I have not seen any come in, but if you have any, please put them in the chat and one of our presenters will address them. If you also have questions after this webinar is over, you are welcome to email us. If there's no questions, I'll take a minute and show everyone where the tutorials with the project files and data that our presenters use. That way you can follow along or recreate the projects if you'd like. So I'm in our tutorial and guide space. I got here from the HMS docs and then tutorial and guides. Jay mentioned the dynamic surface method. So that's under new tutorials to check out. That's a relatively new method here. Pack and Lee dynamic surface method for post-wildfire hydrologic modeling. The reservoir volume reduction is located under modeling reservoirs in HEC-HMS. So that's a whole section about modeling reservoirs. And then David just talked about debris yield methods. That's down here, applying debris yield methods. And he also talked about the ensemble analysis. So you're welcome to grab those files, follow the instructions. And we had one question come in. Any thoughts on modeling the transport of bigger cobbles and boulders?
If you want to model bigger than gravel, then you need to choose the HEC-20. HEC-20 cover up to cobble and boulder.
All right, we'll stick around for the last few minutes till we reach the top of the hour. If you're dropping off, thank you for joining us, and be on the lookout for our next quarterly webinar in March of 2024. Thank you all. All right, we got a question from Steve. Is there any way to incorporate woody debris?
It's not by grain size, but in terms of total volume, because this kind of equation is empirical, based on the total volume. So maybe we cannot generate this woody debris in terms of gradation, but some indirectly we can represent this woody debris in terms of a volume. But that's based on your site kind of information, like some site visit or some sampling, and then you can adjust your volume to account for wood debris. That's my suggestion. But if we have some more specific case, I can kind of talking a little bit more detailedly with you. Thank you.
All right, thank you everyone again. It's top of the hour here, so we're going to sign off. We'll look forward to seeing you on the next webinar. Take care.